Good morning, everyone. We are from JLTH, and today we are presenting our internship project titled Build a Real-World EV and ADA System, completed during our 4-week embedded systems internship at Emerging Information Technologies. Our team consists of Chandana, Lakshmi Bhavani, Sai Mahati, and Rishmi. During this internship, we learned industry-oriented embedded system development using the STM32 microcontroller and applied those concepts to build a working ADS prototype capable of obstacle detection, driver alerts, and URT-based monitoring. Internship overview and learning objectives. This internship was designed to bridge the gap between academic learning and real industrial embedded development. Over 4 weeks, we learned embedded C programming, STM32 microcontroller programming, peripheral configuration, sensor interfacing, and firmware development. The primary objective was to design a real-time advanced driver assistance system or ADAS capable of detecting nearby obstacles and warning the driver accordingly. Apart from technical implementation, we also followed an industrial workflow that included planning, coding, debugging, testing, and validation. Technical skills and tools acquired. Throughout the internship, we gained practical experience with several embedded technologies. We used embedded C for firmware development and learned STM32 peripheral programming, including GPIO, rapid, kindness, and ADC. We also use the STM32 HL library, which simplifies peripheral programming while maintaining portability. For simulation and testing, we worked with Fixing Lab, while STM32 Cube IDE was used for coding, debugging, and flashing programs for the microcontroller. Finally, Python and VSP were used on the PC side to visualize URT data and monitoring the system in real time. Project 1. Our capstone project was to develop a low-cost EV and ADA prototype. The motivation behind this project is that modern vehicles require reliable vehicle detection and driver warning systems to improve safety. We use the HCSR04 ultrasonic sensor to continuously measure the distance between the vehicle and nearby obstacles. Based on the measured distance, the STM32 control generates different warning levels using LEDs and buzzers. Additionally, the measured data is transmitted through URT to a Python dashboard for real-time monitoring. The hardware mainly consists of STM32F103 microcontroller, HCSR04 ultrasonic sensor, LEDs buzzer, and USB UART communication mode. System architecture. This slide illustrates the complete architecture of our system. The HCSR04 ultrasonic sensor continuously detects the distance to nearby objects and sends the echo signal to the STM32 microcontroller. The STM32 processes information using the firmware logic. Depending on the measured distance, the controller activates the LEDs and the buzzer to provide visual and audible walks. At the same time, the process information is transmitted through UART, where a Python dashboard displays the live distance, warning state, and system status.
And then I'll explain how our system works. First, when the system starts, the STM32 microcontroller initializes all the required peripherals like GPIO, timer, and UART. Then we'll read sensors, that is HCSR0 ultrasonic sensor, which sends an ultrasonic pulse to detect any obstacle. The sensor receives the echo signal and the timer measures the timer taken by the pulse. Using this time, the STM32 calculates the distance. Next, the distance is compared with predefined values to check whether the obstacle is in safe, caution, or danger zone. Based on this, the system turns on the appropriate LED and buzzer. At the same time, the distance and system status are sent to PC through UART and displayed on dashboard. This process keeps repeating continuously so the system monitors obstacles in real time. Now, coming to the key features implemented in our project are: first, the system continuously detects obstacles using the ultrasonic sensor. Depending on the distance, it gives three types of warnings. Green means safe, yellow means caution, and red means danger, which usually called as driver assistance alerts. The buzzer also changes according to how close the obstacle is. Another feature is fault detection. If there is any sensor or communication problem, the system can identify it. Measure distance and system status are also sent to Python dashboard through UART so we can monitor everything in real time. We can also change the distance limits easily by modifying the threshold values. While developing this project, we faced some challenges. The first challenge was configuring the STM32 peripherals correctly, especially the timers and input capture. We also had some UART communication issues like baud rate mismatch, but we solved them by debugging the code. Sometimes the sensor readings were not stable, so we used a moving average filter to improve the accuracy. After development, we tested each part of the system. First, we checked the GPR pins and LEDs, then we tested the sensor using known distance, then we tested the whole system. Applications and learning outcomes. This project can be used in many real-time applications in electrical vehicles. It can be used for parking assistance and obstacle detection. It can also be used in ADAS systems to improve driver safety. In industries, similar systems can be used for machine safety and automation. During this internship, I learned embedded C programming using STM32. I gained practical experience in configuring GPIO, timers, UART, and sensors. I also learned debugging techniques and how to send real time data to a PC dashboard. To conclude, we successfully developed a real time EV and ADAS prototype using the STM32 microcontroller. The system detects obstacles, gives visual and sound alerts, and sends live data to a PC dashboard through UART. This project helped me improve my knowledge of embedded system sensor interfacing, STM32 programming, and debugging. Overall, this internship gave me valuable hands on experience and increased my confidence in developing real time embedded applications. Thank you.
Now, I'll explain the firmware architecture and how each module works together to implement the EV and ADAS system. At the beginning of the program, these header files are included. Each header represents a separate software module. Instead of writing the entire application in single file, the project is divided into modules such as AV controller, ultrasonic, ADAS, and UART communication. This modular approach improves readability, debugging, and future scalability. This structure stores all the vehicle-related information such as speed, battery state of charge, temperature, torque, or drive mode. This structure stores the ADAS information including obstacle distances, collision warning, blind spot status, and time to collision calculation. This structure keeps tracks of all system faults such as over temperature, low battery communication errors, and collision-related faults. The first function executed is HL init. It initializes the STM32 hardware abstraction layer, preparing the microcontroller for peripheral operation. Next, the system clock is configured. The clock determines the operating frequency of STM32 and ensures that timer, UART, and ADC works with accurate timing. Here, the GPIO pins are initialized. These pins control the LED and communicate with external hardware. The ADC peripheral is initialized to convert analog voltages from sensors such as the accelerator pedal, brake pedal, battery level, and temperature sensor into digital values. This initializes UART communication, allowing the STM32 to send real-time telemetry to the Python dashboard. These timers are configured to generate precise timing events. Different timers are assigned to different tasks, such as updating the EV controller and reading ultrasonic sensors periodically. This function initializes the EV controller module default values such as vehicle speed, battery level, and the operating mode assigned. The ADAS module is initialized. All the warning flags are up and obstacle distances are reset before normal operation begins. With these lines, the fault manager initializes all the fault flags so the vehicle starts in healthy state. This line initializes the ultrasonic sensors used for obstacle detection. Finally, the UI communication module is initialized so the telemetry data can be transmitted to the computer. After initializing, the program enters the main execution loop. From this point onwards, the firmware continuously performs sensing, decision making, and communication. This condition checks whether the EV update timer has expired. When the flag becomes active, the firmware updates vehicle parameters. Here, the analog sensor values are read from the ADC. Using those sensor values, the EV controller calculates speed, torque, battery state of charge, motor power, and the main driving range. Finally, the latest vehicle status is prepared for transmission. This condition, this channel executes every 100 milliseconds and handles obstacle detection. This function triggers all ultrasonic sensor and measure obstacle distances. Measure distances are processed by the ADAS module to determine collision warning, blind spot alerts, and parking assistance. After the ADAS analysis, the fault manager verifies whether any unsafe conditions exist, such as over temperature, low battery, or critical collision. Finally, all process information is transmitted through UART to the Python dashboard. Apart from the main execution loop, this file also contains several callback functions. These callbacks are automatically executed by STM32 HAL whenever a hardware event occurs. This callback is triggered whenever a complete UART message is received. It processes incoming serial data, allowing the STM32 to receive commands from the PC or Python dashboard without continuously calling the UART peripheral. If the firmware encounters a critical initialization or runtime error, the control is transferred to the error handling function. This helps prevent the system from continuing in an undefined state. Now that we have understood how the main application coordinates the entire firmware, I'll briefly explain the responsibility of each software module. EV controller. The EV controller is responsible for vehicle simulation. It reads accelerator, brake, battery, and the temperature inputs from the ADC. Then calculates vehicle speed, motor torque, battery state of charge, power consumption, and driving range. Ultrasonic. This module interfaces with the HCSR04 ultrasonic sensor. It generates trigger pulses, measures echo duration using timers, calculates obstacle distances, and provides the measured distances to the ADAS module. ADAS. The ADAS module analyzes the measured distances to detect the collision risk, blind spots, and parking assistance conditions. Based on the predefined threshold, it generates warning or critical alerts. Fault. The fault monitor continuously monitors important vehicle parameters such as temperature, battery level, and collision status. If any unsafe condition is detected, it activates the appropriate fault flag and transitions the vehicle into safe condition. UART. The UART module handles communication between STM32 and the computer. It transmits vehicle telemetry such as speed, battery percentage, temperatures, obstacle distances, and warning messages to the Python dashboard. It also receives commands in the PC. Next comes the EV dashboard. The Python dashboard receives the UART data, passes the incoming telemetry, and displays it in a graphical interface. It provides a real-time view of vehicle status, battery level, speed, obstacle distances, and ADAS warning. Overall, the firmware follows a modular architecture. Main.c coordinates the execution while each module performs a dedicated function, such as vehicle control, obstacle detection, fault management, and UART communication. This modular design improves readability, debugging, and future scalability.
So you can see the Pixim lab. And also from the command prompt, I've given the command of Python ev dashboard.py port com1. And I've used com1 because it was said that you cannot use the same com for both the Python and the STM32. So we have taken two separate comms with the baud rate of 15,500. And as we see, this is the Python EV/ADS dashboard. You can see all the parameters, EV metrics like torque, acceleration, brake, and resolve. Now, if we see it in a closer look, we have, as we change these values, the EV dashboard also changes. Yeah, and we have these, as you can see, the battery is green and the alarm is also changing according to the parameters now, and we see the red light, also the yellow lights from the LED sense. We have the potentiometer there. If I increase that, you can see that the yellow is being active, and also it goes for the same way. It is being shown critical. The alarm is showing critical now. If I apply the brake, you can see that the brake is being 100%ly applied. Yeah. And if I do, that is the acceleration potentiometer, and I've decreased it, so you can see the acceleration being to zero. And as you can see, the torque is also zero, the speed decreases. That means your vehicle is not moving anymore. And if I go to the SOC as well, if I decrease it and increase the temperature, you can see the alarm is normal and the mode is normal, but the acceleration is zero. Then with a similar thing, if I change all these front, left, and right car obstacles, you can see that it's being changed, and you can see all those. You can also see the speed history of that here. And if I increase the acceleration again, once again, now you can see the exact more of the parameters of it. You can also see now it's being changed. So yeah. So this is the complete demonstration. This project demonstrates the integration of EV monitoring and basic ADAS features in such single dashboard systems. It provides real-time information to driver and improves safety through obstacle detection. The system is scalable and can be enhanced with additional smart vehicles features in the future. Thank you for your valuable time.